Welcome, dynamics students. This is the last in our demo problems for rigid bodies in planar motion and kinetics considerations, both kinematics of acceleration and the forces and moments that produce it. And this problem is being drawn from the Hibbler 14th edition, problem 117. And in this case, we have a beam with a weight. It's being suspended, and it has weight W. And it is originally suspended from 2 points, A and B. And those points add up to basically a quarter of the way from either end, over 4. And at some point, it's initially hanging evenly. So it's hanging evenly, and it's non-moving. So we can say we have an initial condition no rotational velocity, and we can also, I guess, say Vx and Vy are both 0 initially. It's initially at rest. And at some point, this gets cut. And we also have some other. It is a uniform beam. Other key piece of information. So that means our center of mass is right dead center in the middle if we're looking at our x-axis being here and our y-axis being upward. So we just establish our coordinate system and directions for positive and negative rotational and translational acceleration. Okay, so we're asked basically what is the tension in this cable, in cable A, immediately after cable B snaps. So again, we have a single point in time with no angular velocity, no velocity of anything else yet, but a whole lot of acceleration because we're definitely not in static equilibrium anymore. And under those accelerating conditions, we need to know what one of the supporting forces is. So armed with that information, and we're gonna learn this in terms of the beam weight and length. So we don't have to do any fancy calculations this time because we can do everything in terms of just L and W. So we will say this. We'll say that this is T here at point A. We're doing an FBD of the beam. We have the weight of the beam coming down there. We got another L over 4, and then we have L over 2 going to the end of the beam. We have no other forces. So we can say the sum of the forces in the X, there's no forces that are being exerted at this point, equals 0. ACMX. So at this point, the center of mass of the beam has no reason to be accelerating in the x direction. That's going to change very quickly as it starts to rotate a little bit, and then all of a sudden, T and W are going to be pointing a little bit sideways maybe, but at this instant, no. We can look at the sum of the forces in the y, and those are going to equal T minus W, and that's going to be equal to the mass times acceleration of the center of mass in the y. And we can note here that W equals m times g, so we can use g. And now we can take a look at moments. And the easiest place to look at moments, again, is where we have an unknown force, where it's common to statics in that case. So we're going to take a look at the sum of the moments about point A, and we can write that as just being, with our sign convention, is going to end up being negative L over 4 times W. And that's going to equal the moment of inertia of the beam about point A times alpha. So now we get to use the parallel axis theorem in a little bit unconventional way to figure out what that moment of inertia is. So we could look up IZC and then add the mass times that r, because here's point A. It's a quarter of the way along. Or we can take a look at, we could look up the mass, or the moment of inertia about the end, and subtract the mass times that radius, which is L over 4. So in this case, it depends on which number we can find in a handbook easier. So as it turns out, doing it either way, we end up getting IA or IZ, so it's polar, so we're talking about rotation with the rotation out of the plane of the screen. We end up with, applying the parallel axis theorem, we end up with this expression for IZA times 7/48. It's an odd number. And I believe that came from adding IZC plus the mass times L over 4 squared. And so again, IZC, that would be a handbook lookup, is this whole expression. So again, now that we have what is effectively a number, because we will assume we're given W, we need to solve the problem in terms of W. G is another constant that we can include in our answers if we need to. And we do have a value for the sum of the moments about A. So we can say negative L over 4W equals W over G times L squared times 7/48 times alpha. So do some algebra and cancel as many terms as possible, including W and one of our L's. And so we end up getting an alpha in terms of our gravitational acceleration. We end up getting a negative g over L, which already is good. That gravitational acceleration is in meters per second squared, or some length per unit time squared, and L is definitely going to be in length. So we're already in that per second squared appropriate units. And then we end up with a 12/7 multiplier equals alpha. So the next question is, how do we relate alpha versus acceleration of the center of mass? And once again, we have lucked out in that at the instant in time, we know that we have a point here that, because it's hanging on a non-stretching cable, is a bit of an instantaneous center of zero velocity. It's not a fixed pivot, but at this particular moment in time, it isn't moving. and it's not accelerating because the cable is not swinging at this point. There's no applied force. There's nothing else that would cause an acceleration. So we can treat A as a fixed point at this point. So we can basically, if we apply our our ACM equals acceleration of point A plus alpha R A to the center of mass radius A cross plus omega squared R A to the center of mass. That was 0 because we started with 0 initial angular velocity. The radius vector from A to the center of mass, in this case, is just going to be L over 4 in the I hat direction. Alpha is pointing into the board, so this is going to be in the negative k hat direction. So basically our acceleration of the center of mass is going to be pointing straight down, and then it's going to be all in the j hat direction again, because at this point in time we can say that is also 0. So that's really our key relating alpha, which wasn't too hard to get with the sum of the moments and a parallel axis expression to get IA, using point A as our rotation. Again, it's not a fixed pivot, but at this instant we can treat it as a point of 0 velocity and a point of 0 acceleration right at this moment. So ACM, acceleration of the center of mass, in the y is just going to equal L over 4 times alpha, and that's going to be downwards. And that ends up being negative g times 3. Oops. Times 3/7. And now we have something that we can again insert up here. We have the weight, we have the mass in terms of the weight in g, so we can say that the tension in the rope, the cable at A, is going to equal W plus W over G times negative G times 3/7. The G's cancel, and we end up just getting 4/7 times W at that instant. Definitely doesn't stay that way, but that ends up being the answer to the problem. So hopefully you've seen a pattern in all of these rigid body planar motion kinetics. Again, this was somewhat simpler than others in that we were able to find a point that had 0 acceleration at the moment of a concern. The next increment of complexity would be if we didn't have any points that weren't accelerating, but we had some relationship between alpha and one of the points that we knew was accelerating, or we knew the acceleration at one point. And then we would have a basis to work back through and calculate alpha and maybe the acceleration of another point. But in every case, what's common in all of these problems is that we will be relating a rotational characteristic through a moment of inertia that is applicable to the whole rigid body. Moment of inertia is calculated for the whole body, to the sum of the moments, and then using that rotational acceleration, use the kinetics of the problem to solve for the linear acceleration of the center of mass. that's going to be common to everything. So if we have one point where we can relate center of mass to a zero acceleration of another point, that's great. But otherwise, we will just have to use a couple of more equations to get the information we need. The same procedure definitely applies even if we don't have any fixed point of zero acceleration. But it is, again, essential, write our FBD, understand the net forces in every direction, and then understand that those linear forces in the x and the y, or whatever plane in which we're undergoing planar motion, those are going to apply to the center of mass, and then our rotation will be related to the sum of the moments and the angular acceleration of the whole body. And last but not least, in these cases, we have used a point off of the center of mass to relate the rotational acceleration alpha to the sum of the moments. If we don't have a point of a fixed zero acceleration, it is better practice to use the center of mass as our point for the sum of the moments and alpha calculation. So if this beam had been swinging, moving downwards at a different point, if that cable had been stretching such that we couldn't say that A was fixed, we would have used the center of mass for M. That is just safer practice generally. We used a simplified A to simplify the problem. It was valid here. But if you are in any doubt, go ahead and take the sum of the moments about the center of mass of the rigid body. You'll then use the moment of inertia specific to the center of mass, which is usually a little simpler, and then do the rest of the problem exactly the same. So that is it for this demo, and hopefully you have an idea of the flow of how to apply your kinematics, acceleration of 2 points on a rigid body, and apply the kinetics of rotation, use the moment of inertia to connect what we know about rotation of that whole rigid body to the translational motion of center mass. And that's something that's going to be common all the way through your study of dynamics.